All right, let's continue with our lectures from yesterday. Just give me a second. I'm not even sure if anybody watches these Zoom sessions. So let me just give me a minute while I. This Zoom session is not meant for you guys. It's meant for a group of students who are supposedly stuck in some of the islands out there, and they were not able to make it. I think Solomon, Vanuatu, Samoa. Yeah. And in reality, I do encourage you guys to make sure to attend the lectures here, right? All right, guys. Okay. And as we see, there is only me. All right. Okay. So what were we looking at yesterday? We were looking at conversion from binary to octal. By the way, have you had this today's group? Have you had your tutorial for today? No, only yesterday's group, right? So there's one lot of tutorials today, and there's another lot of tutorials which are coming up tomorrow. Okay. So yesterday we learnt about. Let me just turn the lights on for this. Right. Yesterday we learnt about conversion from binary to octal. Conversion from binary to octal, right? And I showed you a method. I showed you a method of how to go about doing the division and partitions. All right, let's have a look at another example. So today's date is, so today we are in week 2, lecture 2, and today's date is 30th, am I correct? Yes. Okay. All right, let's look at an example number 2. In example number 2, let's now consider the number what did we do yesterday? 320. So let's consider 7, 5, 1 base 8, and let's convert that now. Okay, 751 base 16. So the first thing we've got to do is convert 751 base 16 into decimal, right? And then from there we've got to go into binary. For now. Soon I'll show you a faster method, right? For those of you who did the tutorial yesterday, you would have an idea. So 751 is 7 times 16 to squared plus 5 times 16 to the 1 plus 1 times 16 to the 0. And what do we get, guys? Anyone? Give me the final answer in base 10. 1873. That's it. 4-digit number in base 10. Now 1873 base 10, can you convert that into binary? Can you convert that into binary, please? Right, so I'm taking you the long cut, but soon I'll show you there are other methods. Right, very quickly, I won't do the calculations here because you're very strong with this now, especially after having done all the tutorial problems. You should attempt the tutorial problems. (1873 base 10), we want to convert, so you do a divide by 2, take the remainder. Divide by 2, take the remainder, right? Don't wait for me. I want you to attempt this. So this is what we will be doing in lectures. We'll be doing a lot of in-class exercises. We call this an in-class exercise. All right, answer? Answer? In binary. Answer in binary. 11, 111, 4 ones. 01, 01 again, 000, right? 1. So you have 111, 01, 01, 0001. Right, okay. Now the objective of the problem was to convert to octal. The objective of the problem was convert to, the objective of the problem was, what does it say? Convert to octal. Convert to octal. That was the objective of the problem. So we rewrite our problem: 111, 01, 01, 0001. Now, as you recall, our octal is 2 to the power of 8, which is groups of 3. Sorry, 2 to the power of 3. Right? 8 is equals to 2 to the power of 3, which is groups of 3. So we start from this side. We have line there, line there, line there. And what we do is we just put a filler of 1. Now 001, here padding of 1. We have 1, 010 is 2, 101 is what? 5, 011 is 3. So therefore we learn that 751 in hex is the same as 0111, 0101, 0001 base 2, which is same as 3521 in octal. All right? Okay, let's now move to another topic now. Let's move to another conversion. Let's convert, and you'll find this very easy. We want to convert hex. Sorry, what are we doing? We want to convert binary to hex. Binary to hex. Same concept applies. The same concept applies. Let's now take an example. Let's use the same number. Let's use the same number. Let's try the number 1873, right? Okay, so if somebody gives you 1873 in base 10, and as we are already aware, 1873 is equals to 1110101 from our previous learning, 01101010001 in binary. So whatever number you've got, you're bringing it into binary, right? In fact, I should have given the example one should have been a binary number. But anyway, you guys get the point. Then what we do is we learn, we are aware that hex is base 16, and 16 is equals to 2 to the power of 4. So therefore, we've got to do it in groups or partitions of 4, okay? Groups or partitions of 4. So let's rewrite that number, 0110101001001. Have I written it correctly? Have I written it correctly? All right, so let's do partitioning of 4. Start from this side. Start from that side, okay? Start from LSB, least significant bit. Right, so let's partition. 1, 2, 3, 4. 1, 2, 3, 4. In fact, there was no 0, so we had to fill this 0 up. That's 0 filled up. Okay, 00001. Remember, we had to memorize at least the first 32 numbers or something I mentioned early on, from 0 to 32. So 00001 is what? 1. 101 is 5. 111 is 7. So therefore, what we find from this example is 1873 base 10 is equals to 11101010001 in base 2, which is same as 751 in base 16. All right? Okay, let's do another example. Let's do another example. Let's take, have we done another one? Let's mimic another one over there from the other side so that we can convert. Example 2, let's look at example 1. What was this one here? 320. Okay, so am I in the right place? No, I'm here now. 320 base 10. So this will save us time. Can you call out from our previous example? Can you call out from our previous example, what is the binary equivalent of 320? 101. 6 zeros, 1, 2, 3, 4, 5, 6, base 2. So obviously the same procedure applies. We rewrite it nicely and neatly. We rewrite it as follows. 1, 0, 1, 1, 2, 3, 1, 2, 3, right? Then we have pull down over here, pull down over here, 1, 2, 3. All right, so we have 0, we have 4, we have 1, right? So we have 320 base 10 is equals to 1, this is fill over here, that's same as 101 and then followed by 6 zeros, base 2, which is same as 140 base 16. Okay? All right, now let's do another conversion. Something easy now. So everyone with me over here, what we've done, it's very simple and straightforward. So you see the pattern, to the power of 3, to the power of 4, right, in terms of base 8 and base 16. All right, let's now move to another conversion. All right, so we want to convert the other way around now. Convert from octal to binary. This is easy. Okay, let us take the number, anything which we can reuse or recycle. Okay, this one, 7031 base 8. That's from somewhere early on. We did it. I can see it over here. 7031 base 8. 7031 base 8. Right? Okay, and we want to convert that to binary. Earlier on, if you look here, I don't know which week, which one was this, week 2, lecture 1. When was that? Yesterday, right? We did 7031 base 8, right? And we've got the answer here. We've got the answer along that side there, right? Okay? Now, this is why lectures are important. If you miss one lecture, I will keep on referring back to a previous lecture. If you miss one, you'll start to get confused. What is this guy talking about, right? Okay, now 7031 base 8, we've already found the answer during using a long cut. Let me show you the proper, faster method, right? So what we do is we write it out, 7031. We just partition. For each of those partitions, remember in week 1, lecture 2, I have already mentioned that if you've got to memorize from at least 0 to 35, 30 plus, 32 plus, move above 32. You've got to memorize each and every binary number, right? So if somebody says number 7, you should know, oh, it's 111. If somebody says 14, you say 1110. It should be on your fingertips, okay? If somebody says 16, you say 1 4 zeros, okay? All right, you should know this off by heart. So 1, remember, over here, it's base 8, right? Base 8, and 8 means 2 to the power of 3. So you have groups of 3 bits, all right? So 1 in 3 bits, 0, 0, 1. 3 in 3 bits, 0, 1, 1. 0 in 3 bits, 000. 7 in 3 bits, 111. All right. Okay. The way to avoid confusion is when you read out a number, right? If there's a sequence of, let's say, 3 zeros or 3 ones or 2 ones, you don't say 1 1. You say 1 1, 111. Okay. All right. Or 4. You say 4 ones. Okay. So anyway, in the end, 7031 base 8 turns out to be 111, 000, 011, 001 base 2. And does that confirm with the answer which we found yesterday using the long cut? Does that find the same answer? Yes. All right. Okay, let's recycle another example. Let's recycle another example. 320, have I done 320 already? Okay. Convert from octal and maybe update the title, and from hex to binary, right? Okay, from hex to binary as well. Right, let's try this one here, ACE. Right, so do you see, example 1 is in fact, you know how we went from binary to octal earlier on? We just finished from binary to octal and binary to hex. In fact, this is only doing a reverse gear of the same thing. All we are doing it is we're mapping the other way, right? So the map goes both ways. But where people make mistakes is that they leave these zeros out and they just write 1. So you've got to be very neat. You've got to be very neat. You've got to be very graphical. Try and rewrite, whenever you get the question, rewrite it out with some gaps so that you have enough space to plug in the bits. Okay? All right. Now, ACE is in base 16. Now, base 16 is 2 to the power of 4. So 4, we have groups of 4 bits. Okay. So you have ACE. Write down A, C, E. Dot, 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 dot. Okay. What is E? E will be? Yeah, no, in bits. Yeah, 1110? No, not 0111. If you say 0111, that's 7. Right? 1110 is E. Okay. What is C? C. A. Therefore, ace in base 16 is equals to 1010, 1100, 1110. All right. So that's very straightforward. Okay, so you don't really, in my earlier example maybe, especially the one for example 1, what did we do? We went from 7031 base 8, we converted to decimal first. From decimal, then we did the divide by 2, take the remainder, and we collected all the remainders, then we went to binary. So using this method, from octal and from hexadecimal, you can do direct conversion. But if I give you an imaginary base, let's say if I say something is base 9 or base 11, right? In that case, you can't do direct conversion to binary. I mean, direct conversion to binary like what we've done. We've got to go through, you've got to go through base 10, and then from 10, you convert into hexadecimal. I mean, convert to binary. All right, now, let's now do another one. Convert hex to octal and reverse. All right, let's recycle our earlier example. What did we do earlier on? Somewhere over here. Right, 320. Oh, no, this one. 751 base H, yeah? (751). And the way we did it earlier on was, sorry, yeah. If you look at this example, we went from 7.51 and then we eventually found 3521. But we had to go via 751, we went to decimal, so we went from octal to decimal, from decimal to binary, from binary to hex. Yeah? Okay, so I show you now a faster way of doing this 751 problem. So 751, we will rewrite it as so. 751, we draw our partition, and we are going from base 16, we have to first stop at binary. So in the past, how many stops did we have to do? We had to go from octal, sorry, hexadecimal. Hexadecimal to decimal, that's the first stop, right? Then from hexadecimal, so from decimal to binary, that's the second stop. Then from binary, then we went into octal, that's the third stop. So we had to do 3 stops. So in this one, it'll be much faster. So 1 in 4 bits, because we're going into binary now. 0001, 5, 0, 1, 0, 1, 7, 0, 111. So we find that 751 base 16 is equal to 0, 111, 0, 1, 0, 1, 0, 0, 1 base 2. So we now rewrite this now. 0, 111, 0, 1, 0, 1, 0, 1, right? Over here, the catch was that we were doing 4 bits, right? Now, we have to partition into 3 bits because our eventual destination, maybe I should have written the thing, convert to octal, eh? Right. Now we partition into 3 bits. 001 is 1, that is 2, that is 5, that is 3. So we find that 751 base 16 is equals to 3521 base 8. Right? And does that correct? Does that contra with the answer in the previous section? Right. Let's now do another one. Let me give you 4, 7, 6 base 8, and I want you to convert it to hex. Right, so I'm going to give you a bit of time. You can speak with your neighbor or whoever you want to speak to and discuss and do this problem. So the first step over here is, well, the main point I forgot to mention in our earlier problem is that it was a single stop in the middle. We went to binary, and from binary we went to the answer. And in the previous case we had 3 stops. We had to go via 3 other different bases eventually to find our final answer. So what we're going to do over here, we're going to convert to binary, right, by doing direct conversion. From binary we will re-partition. Right. Okay, so write it out. All right. For 476 base 8 is equal to what is it in binary? So base 2. Is that correct? No? Oh, sorry. I've considered that as base 16. So sorry. There'll be 100, 111, 110. Right? That's correct now? Yeah. 4 is 100, 7 is 111, and 6 is. Okay. Then what do? We have to repartition. And when we repartition, what do we get? Triple 10 is what? Sorry, what do we get, guys? 1 A. Oh. E for elephant. All right. Okay. There we go. 1 3. And if you don't know how I got there, then you are in trouble. Okay? This is probably one of the easiest problems which we are going to attempt, because it's easier now. In the past, the examples which I did yesterday, we went through a long cut. This is much more easier, much more faster. And if you don't know how to read and convert very quickly, look at me. I didn't have to. When I went from here to binary, I didn't have to do much. I just had to look at the number, and it was downhill from there. Okay, guys. All right. Let's have a look at our next particular topic. So we've looked at a bit of number systems. So if I give you an imaginary number system saying, hey, I've invented a new number system which is base 6. You should be, and I say, I want you to convert this base 6 number, right, to octal or to hexadecimal. You should be able to do that using whatever knowledge I've given you, because it's the same concept. You'll go from base 6, you'll go into maybe decimal, and from decimal to binary, and binary to then to hexadecimal. All right, okay, because base 6 you can't do direct conversion. But if it's octal or if it's hexadecimal, then you can link between, convert quickly between binary and hexadecimal or octal very fast. Right? So that's the advantage of octal and hexadecimal, because conversion to binary is very fast and efficient. Okay. Right, guys, let's have a look at addition in binary. Let's have a look at addition in binary. All right, in decimal. If we have, let's say, let's choose some number. Let's say 2, 4, 7, right? 2, 4, 7, and we want to add, give me another number. Let's say 3, 6, 5. What do? We say 7 plus 5 is 12, 2 carry 1. 4 plus 6 is 10, plus 1 is 11. 1 carry 1. 2 plus 3 is 5, plus 1 is 6. So do you notice that when the sum is done, if you have an extra digit, we do something called a carry. Okay, fine. Now let's look at example 1 in binary addition. And when do we get that extra digit? Well, in decimal, we only go from 0 to 9. If 7 plus 5 is 12, 12 is greater than 9. So therefore, you store one digit and you move the carry upwards. Okay? All right. Now let's have a look at binary addition. Let's try 1001 plus 1101. Okay, maybe 0101, right? Maybe start off easier. All right. So we have 1 plus 1 is 1, 0. 2, which is 1, 0. So you put 0, carry 1. You put that 1 down, right? 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 1 is 1. Base 2. Right? Now, in the meantime, let's look at the decimal equivalent. 1001 is what? What in decimal? 1001 is 9. And 0101 is what? 5. 9 plus 5, we should get 14. So does 1110 equate to 14? Yes. So we know our answer is correct. Now let's look at example number 2. Let's start off with 1101 and let's add a bigger number. Yeah, thank you. Let's add a bigger number. Let's say 0111, right? And let's see the equivalent. 1101 is what number? 1101 is 13, and 111 is 7. So we have 20. We are expecting the number 20. So let's do this in binary now. 1 plus 1 is 1, 0. Put a 0, carry 1. 1 plus 1 is 1, 0. Put a 0, carry 1. 1 plus 1 is 1, 0. Plus another 1 is 1, 1. Put a carry 1. 1, carry 1. 1 plus 1 is 1, 0. So we eventually end up with 10100. If you now do a direct conversion, that's 1, 2, 4, 8, 16. 4 plus 16 is 20. Yes, that works out to be correct. However, if the system is 6 bits, sorry, not 6 bits, 4 bits. 6 bits is your tutorial. All right. If your system is 4 bits, then let's look at the answer. This would become overflow, and this would be stored. So 0100 is equal to the number 4, which is definitely not equal to the expected answer of 20, right? So therefore, we get the wrong answer, all right? Okay, so unless the question says, always assume that the least significant bit is stored, all right? Otherwise, unless it says, hey, in this system, only the most significant bits are stored, or in this system, no bits are stored if there is an overflow, all right? Like your calculator, your FX82 calculator, the moment there is an overflow, if there's an error, it will just give you an error. You just say error. It won't go and give you the wrong answer. You just say error. Okay? All right. Okay. Okay. Now, what time is it? 1:45. All right. Let's do another problem. Let's do another example. Example 3. And let the class handle this. 6-bit number. Can you calculate this and find me the decimal equivalent and what is the correct answer and assume that the least significant bits are stored. Only it's a 6-bit system, right? Just write it down somewhere. It's a 6-bit system. System is 6-bit. So you're supposed to do this on your own. Consult with your neighbor. Consult with your neighbor, or if you know the answer, that's good. So most of our lectures will be like a hybrid between lecture and tutorial. We'll do certain things in class. And guys, before going to the tutorial, you are expected to attempt the tutorial. Don't go to the tutorial expecting to copy off the board. We are not doing online classes anymore. We are actually doing a proper face-to-face class, all right? Okay, so what do we get? And guys, I want you to do the expected answer on the right-hand side. One plus 4 is 5 plus 8 is 13. 32. 13 plus 32 is 45. Is it 45 over here? 1, 2 plus 4 is 6 plus 8 is 4 is 6 plus 8 is 14 plus 16 is 30. 30? Is it 75? Are you expecting 75? Yeah? All right. Okay, now we go ahead and do this. 1, 1, 1, 0, 1, 0, 1, 0. So 1, 0, 1, 1. Does that equal to 75? 1 plus 2, 4, 8, 16. What did I miss? Okay, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 1, 0, put a 0, carry 1. Oh, there should be a 1 over here. Right, 1 over here. Right, that's correct. Yeah, that's correct, that's correct. So where is the 1? Okay, is that correct now? Yes. Okay, so 75. But this is stored. This is the overflow. So what is stored in the end? The number 11 is stored. So that's the wrong answer. All right? Okay? So that's the sort of problem which we are looking at. Okay, guys, we're going to stop writing now. I'm just going to flip over back to the thing. And these sort of problems, even if I flip the page fast, you should be able to catch on very quickly. All right? Because remember, I only have effectively 2 hours and 2.5 hours per week with you. So if I start writing each and everything and waiting for everything, then it will affect our delivery of the course. All right, let's go to Moodle now. I just want to show you, before we finish in the next 5 minutes or so, when you go to the Moodle shell, when we go to the Moodle shell, we have let's look at lecture 1. Okay, so I'm just looking at some of the notes on the lecture on the Moodle shell. What I'm trying to tell you guys over here is that whilst we are doing what we are doing while I'm writing some examples and doing in-class exercises, let us not forget that there are some notes over here, all right? Let us not forget that there are some notes over here, all right? So this is what we have done. You remember when you are doing all the conversions and all that? So a lot of it is repeat. When you look at it, a lot of it is repeat, right? Hexadecimal, nibble, byte. This is all the conversion between all the different types. Okay, there's binary coded decimal. Okay, so this here, binary coded decimal. So these are some notes over here, which there's really no point for me to write again because it's already tapped out. So no point in me rewriting. So what you see me writing in the exercise book, you will not find it. You will not find it on the note. All right. So that is why it is important for you to attend lectures. So anybody who is missing class right now, if you know any of your friends who are missing class right now, because I'm expecting 66 students in class. If anybody who's missing class and they are watching, just following the notes on Moodle, they'll fall really behind because what we do in class, that's crucial. All right. So binary coded decimal is basically binary. Okay, if you have 4 bits, okay, this is a very important point. If you have 2 bits, how many possible combinations? It'll always be 2 to the power of number of bits. So if you have 1 bit, 2 to the power of 1, only 2 combinations, either 0 or 1. If you have 2-bit system, if you have a 2-bit system, maybe you can write it down in your exercise book. If you have a 2-bit system, you have how many possible combinations? 2 to the power of 2, which is 0, 0, 0, 1, 1, 0, and 1, 1, if you draw up a table with 2 bits. If you have a 3-bit system, how many possible combinations? It will be 2 to the power of 3, which is 8. 8 possible combinations. 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, or something like that, right? Okay, so it's 8 possible combinations. You have to write it out. Okay, now if you have a 4-bit combination, the maximum possible limit is 16 combinations. If you have 4 bits, you can do 2 to the power of 4, which is equal to 16 possible combinations, starting from 0, 0, 0, 0, going all the way till 1, 1, 1, 1. What binary coded decimal does is that it goes from 000, I mean 4 zeros, and stops at the number 9, which is 1001. It stops at 1001. All right. After 1001, if you think of the odometer, after 9, it will flip back to 0. So after 1001, 9 in decimal will become 10, right? Or in terms of hexadecimal, if we were looking at hexadecimal in normal base 10, that would become 10. In base 16, this would become A, right? The next digit, right? In BCD, after 9, it won't become A, it'll become 10, 10, because it's still decimal, right? Binary coded decimal. This here will become 1 followed by 4 zeros. It will reset. So the moment it reaches 1001, the odometer resets and becomes 0, right? Okay. So the next number, which is 10 over here, will be not 1010, but 1 followed by 4 zeros. That's a very important point. Okay. Gray code. There's another set of code. So binary coded decimal. Gray code has only 1 bit change in every iteration. So these are different types of code generated by different people. All right. So when you do the tutorial, you'll see that there's certain numbers. For example, fractional numbers. If let's say we are only looking at positive numbers so far, when you look at unsigned numbers, like negative numbers, which we are going to start soon in tomorrow's lecture, right? Tomorrow's lecture is very important because we're going to look at negative numbers. Like when we look at negative numbers, when we look at fractional numbers, let's say if somebody says 5.356, how do you store the decimal point? So different companies have different standards. So for example, IBM has a particular way of storing. IEEE has a different way of storing. Gray code is so everybody has a different standard. So you have to give your answer according to that standard. There's sign in magnitude standard, there's 2's complement standard. So that's regards to negative numbers and fractional numbers. So gray code is another standard, and the standard is that in every iteration, going from number 2 to number 3, only 1 bit changes, not 2 bits. Okay, so that's their gray code. Right? So this is some information. There's another particular code called ASCII, American Standard Code for Information Interchange. This is the code which is used for your keyboard, So when you press a particular alphabet on your keyboard, right, every alphabet or every character has an equivalent 8-bit code, which is 2 hexadecimal numbers. So this is the ASCII table. So when somebody presses, let's say cat, C-A-T. So C-A-T would be C is double F, A is LF, right? And T is, sorry, I was looking at the wrong line. I'm sorry. We have to look at this line here. Okay, C, let us see. Letter C is 4-3, A is 4-1, and T is 5-4. But that's in hex. What is C in 4-3? 4-3 is hex, right? C, so somebody is trying to type cat, C-A-T. Cat would be, C is 4-3. 4 is what? 4 is 0-1-0-0. 3 is 0-0-0-1, right? Okay, then A is